In this video, we're going to talk about writing molecular, complete ionic, and net ionic equations for single replacement reactions. So this is a little bit different than the double replacement reactions we've been doing, where we had to look to figure out what would form a precipitate. In this, we don't have to worry about that, but there's this thing, something called the activity series that we're going to learn about later in the year when we cover redox reactions. But for now, we just have one element displacing another, and in this case, it's a metal that's displacing another metal. So aluminum reacts with copper nitrate, and it displaces the copper to make copper solid and aluminum nitrate. And I just want to point out that when you have a metal that's in an elemental form, it's going to have no charge. But if it's part of an ionic compound, then it's going to be charged. Okay. So when we write out the complete ionic equation, you have solid aluminum metal, and keep in mind you have to use coefficients to account for how many of these ions we have in solution. But you have aluminum, solid, copper, aqueous, and then nitrate as aqueous ions. As products, you have solid copper, we have aluminum as an ion, and then you have the nitrate ions as well. So if we're looking at this complete ionic equation, we can see that the nitrates don't do anything. They're spectator ions. They don't change at all from beginning to end. So we leave them out when we write the net ionic equation, and we can really see what's happening here is that electrons are being transferred from the aluminum to the from the aluminum to the copper as it forms elemental copper. So again, in the net ionic equation, only include the things that are involved in the chemical reaction, not just floating around as ions. So now, we're also going to perform some solution stoichiometry with this reaction. So some questions I could ask, just making up an example, how many grams of copper will form if we have 2.5 grams of aluminum react with 250 mils of 0.150 molar copper nitrate? And then we could do some other calculations, but let's start there. So we write out, when we're writing our mapping, how much of each reactant we have. So you have 2.5 grams of aluminum, that's 0.0926 moles, again using the molar mass. For our solutions, the new piece to the map of mole town is that we can use the molarity equation to rearrange it to solve for the number of moles. So the moles is equal to the volume times the molarity, and we find that we have 0.0375 moles of copper nitrate in the solution. So you take a guess at what's going to be your limiting reactant, and usually you'll take the thing with the fewer number of moles and see if you have enough of the other reactant to perform the reaction. And also in this case, it has a higher coefficient, so it's going to get used up at a higher rate. So should be pretty confident, but let's see if that's how it works out. So if you have 0.0375 moles of copper nitrate, you're going to need 2 moles of aluminum for every 3 moles of copper nitrate. That means that you would need only 0.0250 moles of the aluminum to react with all the copper nitrate, thus establishing that this is in fact your limiting reactant. So we're going to use that to figure out how much product we can make. Since you get 3 moles of copper for every 3 moles of copper nitrate, we would get that same molar amount of solid copper. Then using the molar mass, we could say that that gives you 2.38 grams. So that's how much copper would form. Now some other questions I could ask would have to do with how much aluminum remains. So aluminum, if we had initially 0.0926 moles, we use 0.0250 moles, well, what remains is the difference between those. And then to figure out how much that would weigh, we just multiply by the molar mass, and we'd find that you have 1.82 grams of aluminum remaining. So in your final mixture, you're going to have 2.38 grams of copper, 1.82 grams of aluminum remaining. But what else? Then we look at part C. What's the final concentration of the aluminum nitrate that's formed? So to do that, you could start here with moles of limiting reactant, but we also know that that's going to be the same number of moles as copper we have, and you can relate any two things in a chemical equation as long as you use the coefficients from the balanced chemical equation. So you're going to get 2 moles of aluminum nitrate for every 3 moles of copper, meaning you would have 0.0250 moles of aluminum nitrate. And if we're looking for the final concentration, well, the molarity is going to be the moles divided by the volume of the solution, which was 250 mils, or 0.250 liters, and we would find that the final concentration of aluminum nitrate is 0.100 molar. So this is how we can describe what's happening in an aqueous chemical system if we have a single replacement reaction occurring.